I think that sounds pretty promising. All right, hello everyone. Welcome to today's class of CSE365. We are on the third module, building a web server. This module is due in 6 days, 11 hours, 55 minutes. So you got some time still, but I highly recommend you get started as soon as possible. That way, if you encounter issues, you can go to more recitations, ask more questions, not panic at the end. And of course, always the looming fear that a few hours before the deadline, the server is just like miserable to use. I don't think that happened last assignment, but the fear is there. I'll say that in an upcoming module called reverse engineering, the fear will be very real that happens. But there's still a chance. I encourage you to start soon. Okay, so we have been talking about making a whole bunch of Linux system calls, and we've showed how you can find some of these constant values. So for example, in the case of something like the socket system call, if we look here, right, we have these like values like AF underscore INET, sock underscore stream, IP proto underscore IP. These things are just numbers, as a reminder. I'm going to keep saying that because I think it's unintuitive, maybe. But these things are just numbers, and if there is any difficulty, the difficulty is just figuring out what the heck the number is for AF underscore INET. As we showed, my preferred technique for finding this value is to grep through user include. So user include has a whole bunch of .h files. So when you do pound include inside of C, more likely than not, that header file is coming from user include, though you can provide your own header files not in user include. And these header files, one of them is like almost guaranteed to have this definition because these constants aren't out of nowhere. These are very important constants. And if you're wondering how it works, right, in the Linux kernel source code the source code also has a whole bunch of header files that define these things. So on the kernel side, it has a bunch of constants defined. On user space side, a whole bunch of constants defined. These constants are the same constants, and now that's how we can speak and say AF underscore INET. So for example, if I want AF underscore INET, I always get this backwards. Let's see if we got it right this time. Okay, we got it. So this is, we just grep through, and literally we're looking for the string control F AF underscore INET, the entire user include directory. Well, every time there's referenced, here they are. This is probably a little bit less useful. Instead, pound define is just about always how these things are defined. Unfortunately, AF underscore INET is defined to be PF underscore INET. This is probably some sort of compatibility layer. Probably PF underscore INET was first, and then they're like, that's confusing. Let's also add this constant that is the same thing but has a clearer meaning. I don't know why AF is clearer than PF. I'm not sure what that history looks like, but that's what's going on here. And so now if instead we look for PF underscore INET, we will see that this person right here, x86-64 Linux GNU bits socket.h declares that PF underscore INET is 2. And more likely than not, they're not lying to us. It's probably 2. Start with that. I've never seen someone like grep through this thing and find a definition for a value is like 17, and then it turns out it's not 17. If you encounter something like that, it'd be an interesting story to hear, but I've never heard this method fail. I've never heard like the same constant being defined to be 2 different values, at least not for this module and the important concepts or constants here. Okay. So that means, we want to pass the first argument of AF underscore INET. We want that to be the value 2. So what do? Does anyone know how do we set the first argument to be AF underscore INET? It's one x86 instruction. One x86 instruction to specify the first argument to something is AF underscore INET. Anyone know? Yep, move RDI. Yeah, again, it's not I mean, that's probably kind of a little bit of an unfair question because I'm like now asking you to memorize the first argument's register. You don't have to memorize it. You can reference it. Yeah, the first argument is RDI. So move RDI to is put AF underscore INET in as the first argument. So this is going to be something you do right away. I think on level 2, you're going to make this system call. So this is probably going to be the first thing that you hit that's like, what the heck's going on here? Level 1, I think you just make an exit system call. So, I mean, I guess you got to make sure you know how to make a system call as we've discussed. And then, like, this is level 2, this is level 3, this is level 4, this is level 5, I'm pretty sure. Don't take my word for that, but something like that. And then after that, once we've made a bunch of system calls, we've figured out how to put constants in for values. Then we start, like, actually building up a web server that does something. One other kind of little tricky thing, it's kind of unfortunate how, well, I guess I can, well, zooming in doesn't really work. I can do that, sweet. Yeah, that's way better. The next kind of maybe tricky thing, or like what the heck's going on here, besides constants that you're gonna run into, is what the heck is this curly brace thing? This curly brace thing is the notation in strace that says we're using a struct. And you've probably used a struct before in C. A struct isn't fancy. Maybe it's like a scary word, you know, structs in C or something. All it means is memory laid out in a particular arrangement. So like the first 2 bytes are being dedicated to this, then the next 4 bytes are this, then the next 4 bytes are this, something like that. Sequential memory segmented in a particular way, that is all a struct is. And so if we want to figure out, I think the lectures show what the heck's going on here for making these system calls. Yeah, this right here. So this is the struct called sockadder underscore in. When we make, like this, before we do that, let's talk about this system call. All of the other system calls here, actually we'll go back to the page where we have a bunch of them out here. So these 4 system calls, almost all of them are just passing the value in through an argument, right? I mean, through a register, right? So we're putting something into RDI here, we're putting something in RSI here, we're putting something into RDX here. I mean, that's how all argument passing happens. But we're literally just putting that number into the register. In the bind system call case, though, this first one, sure, we put 3 in as the first argument. And the reason we're putting 3 in is because that's the return value of this, and this thing is taking a file descriptor. Again, we read the man pages if we want to understand what the heck's going on with these arguments. The issue comes with this second argument. This second argument has a bunch of data that we need to somehow convey to the kernel. We're specifically saying that we're binding this INET thing, this AF underscore INET. So this constant comes up again. You can almost think of this as being the type. So if you've, you know, written something in Java or, you know, C++, and you have classes and stuff and you have types, the simple way to convey a type is just the very first piece of this data is just a number that represents the type. That's how typing works. It's very simple, or that's one simple way to implement typing. And so this very first little piece of data that's going to be sitting somewhere in memory is just the type. And then we also want to convey a port. So if we'll get more into networking in a future module, but if we want to listen on some port, we need to specify what port we're going to listen on. In this case, we're listening on port 80. Web servers just about always listen on port 80. That's kind of the default standard port for a web server. You don't have to listen on port 80. You can do a different port, but that's the default. And then we're specifying what network interface, what IP address we want to listen to. In this case, we're saying 0.0.0. Maybe that doesn't look like an IP address to you. Maybe you're used to something like 192.168.0.1 or 127.0.0.1 or a whole bunch of other IP addresses. There's a whole bunch of IP addresses. You know, there's 2 to the 32 of them, at least as a IPv4. 0.0.0 is kind of this special catch-all value that means I want to listen for connections on whatever the heck can possibly talk to me. I want to listen. So the issue here with conveying all of this data is this is more than 8 bytes worth of information. And a register, as we said, can only hold 8 bytes worth of information. You can't store more than 8 bytes worth of information inside of a register. And so instead what we do is we use memory. Memory is like our catch-all for when we have limitations of how much data can be stored, because we got maybe 20 registers or something that can each hold 8 bytes. We got gigabytes and gigabytes and gigabytes of memory. I mean, it depends on the system, but you got a lot of memory. So since we can't fit this all into 8 bytes, it's kind of like the natural thing to reach for is to instead just use memory. And instead of passing by value, we're passing by reference, right? We're passing a pointer. So we're just passing a memory location. And then when the kernel wants to figure out what the heck you're trying to do, it'll just look at that location in memory, and it might start pulling parts of this into registers and doing whatever the heck it needs to do. But it just encapsulates all within 8 bytes because we're just using a memory address. You might also say, I mean, why not just have more than 3 arguments, right? Like we could imagine the second argument is just this thing, and then the third argument is just this thing, the fourth argument is just this thing, this is the fifth argument. You could implement it that way. I'm going to say the simple answer is this is what the Linux definition is. This is what you got to do. So this is what you got to do. Probably like the reason is because this is like a type thing, and you want to like maybe some other family of things doesn't have a port and an address. It has other things, and it's just like it has different sizes to it. I mean, this thing right here is the number of bytes that this structure is. It's just how they opted to implement it. It makes sense, believe it or not, and this is how it works. So what we need to do to convey all this information is just put all this information into memory. So you can see here that we've shown what the heck the structure of this thing is. What is the memory supposed to look like here? This is the definition of the structure. This is what it looks like in C. This is how you would define one of these things in C. And maybe you're not used to this like uint 16 underscore t. Believe it or not, it's way simpler, or in my opinion, it makes way more sense to say this type of thing versus a character versus an int versus a long long. Like what the heck are these things? This is 16 bits of data. This is 16 bits. This is 32 bits. This is 8 bits. Way simpler to convey through this. And specifically also, these are all unsigned values. If the u wasn't there, it'd be a signed value. All these things are unsigned. Yeah. So the first thing here is a uint 16. That means 2 bytes, right? 16 bits, 2 bytes. All we do is put into memory this value. So we're going to write some assembly. If we want to put some data laid out in a very specific structure into memory, we'll show how to do that. But this is what it's going to look like, right? We're just going to have a byte followed by a byte, 2 bytes worth of information. Remember, this is a little endian integer. We already said AF underscore inet is 2. So we put a 2 in and 0, 0 because little endian integer. This is how you represent 2 as 2 bytes. Then we want to represent 80. 80 is also going to be taking 2 bytes because it's a uint 16. So now we have another 2 bytes we need to fill in, and this is going to be the port. We're listening on port 80. It's very unfortunate that we're like teaching assembly and some like networking stuff simultaneously. Almost everything you do, at least in the x86 world, I think ARM also, I don't know. Almost everything you do is a little endian integer. We're using little endian where you put like the least significant byte first. I'm not sure what the history is, but for some reason in the networking world, we operate on big endian integers. So it is the reverse of little endian, where the most significant byte goes first, then the next most significant, so on. It goes the opposite direction of filling these in. Which means if this was a little endian integer, we would put 5, 0, and then 0, 0 to fill in this value, this portion of memory right here. But this is a big endian integer. And the way that we convey that like very clearly is we use this H2NS thing. This means host to networking, not sure what the S is. Basically host to networking. This is a macro within C that it would work if you were on a big endian architecture, so x86, not a big endian architecture. But if you were on some big endian architecture, it would translate it just as it normally would be conveyed, versus if you're on a little endian, it knows to convert, to flip the order of the bytes, basically. And so that's what the heck this H2NS thing is. It basically means turn this into a big endian integer. And the same is true of this other networking thing. So the port is a networking thing. The IP address is a networking thing. This is also a big endian integer. And as we said, this is 4 bytes, uint32, 4 bytes. And so this also gets filled in as a big endian integer. Again, if this was a little endian integer, the 01 would be first, the 7f would be at the end, but this is a networking thing. Networking is basically the only exception for our purposes that follows big endian instead of little endian. And so this is how you fill it out. This makes it a little bit awkward when it comes to doing it in your assembly. So when you're writing your assembly, we'll show this. It gets a little bit awkward to put in a big endian integer. Maybe there's a better way of doing it. But you kind of just flip it yourself, or you can go byte by byte. We'll just do the byte by byte approach to just make sure you're filling this incorrectly. And then the strace view, when we make that system call, ultimately will confirm to us that we did it correctly. And then also this is, remember, this is a type. There's a whole bunch of different type things. So if you're going to have a whole bunch of like polymorphism, right, we're going to have a whole bunch of different things that can fit into this memory. We also have some padding. In the case of AF_INET, we don't need these last 8 bytes. So it's just padding. You put zeros there. I don't think it matters. You probably put something other than zeros there also. It just doesn't matter. And maybe in the future, they decide to use this space, and otherwise, a different protocol might decide to use this space. Okay, so let's go ahead then. There's a question, yeah.
So that's only 7 bytes total in that struct as opposed to 8 bytes?
So 32. What, sorry? So this is 9 bytes, right? 16, so 32 plus 32, 64, so 8 plus 1 more, 9 bytes.
Oh, 66 has 66,
Right. So 16, 32 plus another 32, 64 plus another 8. So this is just pulled straight from the definition of what the heck a sock adder_in is. They've decided that this is the shape of it. Later on, it'd be interesting to see what the heck happens. Later on, we specify, is this, well, I guess, hold on, let's see here. What is this third argument? Man to bind. Adder length. Adder length specifies the size in bytes of the adder structure pointed to by the adder. So technically, we're saying this thing is 16 bytes. Oh, I missed it. This is an array of 8 of these things. So the first 3 members altogether are 8 bytes worth of information. Then we pad out another 8 bytes. This isn't just 1 byte. This is, 8 bytes of padding.
Yeah, that's what I did 8 bytes.
Right. So and I guess this diagram shows this. These are all null bytes. So yeah, that's why it's 16 bytes altogether. And the reason for that is just that this is the definition of the structure. If I had to guess, I would say that if you used a different SYN_family, for example, I imagine there's one for like, if you want to start listening on Bluetooth or something, there's probably a different SYN family for that. And that might not even have like port and adder. It might just have totally different things. I don't know that to be the fact. I've never worked with Bluetooth, for example. I've only ever actually worked with AF_INET. But that's why you would do that, is to support this whole thing being able to be a lot larger. Because if we look here, this thing says it takes a const struct sock adder. So a sock adder, I think, altogether is 16 bytes. At least normally, maybe there's extensions to that for further things. That's why we pass this size. But we're not looking at the definition of a sock adder. We're looking at the definition of a sock adder_in. And a sock adder_in, this is how we lay out memory. And I think every single sock adder, the first 2 bytes are just specifying the type. And so when we say AF underscore INET, we're kind of simultaneously saying this is the type to confirm that, right? So this is always going to be AF underscore INET. And then this is what the layout of that is. It's kind of defining both at the same time, the structure and the type, right? So this is how this is implemented. Everything I'm saying maybe is a little more confusing than it needs to be. Really, we're just going to put some bytes in memory, okay? We're going to put 0200, that means AF underscore INET. We're going to say our port, we're going to say our IP address, we're going to fill in a bunch of null bytes, and we're done. We've specified all of this in memory, pass that off to the kernel. The kernel is going to know what to do with this to set up our process for success. Okay, let's go ahead and do that then. Don't save. Let's get rid of all of this. So if we want to lay out memory, and we want to say we have a sock adder, for example, we'll do .section.data, and we'll create a label to specify this is now a referenceable thing. In our actual assembly, we'll reference this label. And if we want to just put these bytes into memory, I mean, the very simple way to do it is if you don't want to mess around, you just want to go byte by byte, we can literally just say .byte 0 to, or 2, .byte 0, right? Now we've got a 2 byte here and then a 0 byte. And then you could do .byte 0, .byte 0x50, or you could say 80. Either way, whatever. This 0x50 is 80. Now we've got 4 bytes laid out in memory. Let's go ahead and just make sure that that is true. We'll make sure that that's true with GDB. We'll run make live. I just realized I think make debug. Nope. Hold on. CD shell copy assembly make file to here, and we'll copy debug GDB to here, make. Okay. So well, I guess the issue is now we don't know where the heck this is located in memory. Let's reference this thing. Let's just move sock adder, the location of that thing, into a register. So move REX, there was a question? Or no, maybe not. Move REX offset sock adder. Right, so we're just taking the location of memory, offset sock adder, and we're putting that into REX. Now we'll be able to look at this in GDB. Make. Okay, so this thing is located at 402.0.0.0. If we look at 4 bytes worth of data at this address, we will in fact see 02.0.0.0.0.050. So we got the first 4 bytes laid out exactly as we said before. And we can just keep doing this all the way. We can go byte by byte. This probably wouldn't be the standard way to represent this, though it is a way that works. So we could say 127.0.0.1, right? So this is 127.0.0.1 as a big endian integer, just laid out byte by byte. And then we would do byte 0. We need 8 zeros. Byte 0, byte 0, byte 0. Oops. Okay, and now we've laid out 16 bytes worth of information, byte by byte. So I don't know, maybe you like this way of doing it. I think it's very clear. It's definitely very clear what the heck these sequential bytes are going to be. This probably isn't how you would find someone writing assembly like this in a traditional way. But that's okay. I mean, it works. Let's see. 16 bytes. Yeah, so 02.00.00.50.7F, right? It's all laid out exactly as we have in this diagram. This is correct. And we can confirm this is correct if we do this system call. We were doing the accept, so, or no, we're doing the bind system call. Technically, we haven't set up the socket, but that's fine. We can still make this system call. This system call is going to fail because it's going to be reliant on the fact that this first file descriptor is a socket, but we can just pretend like, hey, screw it, we're just going to bind to standard in, which isn't a socket. The kernel will yell at us saying you can't do that, but we'll at least be able to see like we did it, like we made the system call, we made the attempt. So if we want to do that, we need to make the bind system call. So we search for bind right here. Bind is system call 49. So we put 49 into rex. We want to put a first argument RDI, which is an int. It's our file descriptor. Again, we're just putting 0 in here. We're going to specify standard in. This doesn't make any sense, but we'll be able to see that we're making the system call. RSI, we'll put offset sock adder because that is our pointer. And then the third one was supposed to be, I believe, when we looked at this, it's the size, which is 16. So move RDX 16. We'll get rid of this REX thing. We'll make a sys call. And this is how we would make this system call. Again, it's going to fail. That's okay. We'll make this. We'll just strace./test. And we will see right here, we made the system call. So we tried to bind file descriptor 0. We did SA_family equals ifnet, syn port equals h2ns 80, syn adder equals inet 8, adder 127001, and 16. I think in the challenge, you don't want to do 127001. I think it tells you to do 0.0.0.0. Turns out that's even easier, but I'll let you figure out how to do that. And in this case, I mean, we're expecting to get a 0 back. We didn't get a 0 back. We got E not sock, socket operation on non-socket. This is exactly what we said was going to happen. We tried to bind to our TTY. We tried to bind to standard in. This terminal we're typing on. This thing is not a socket. And so the kernel said, nice try, but we're not doing that. Does anyone have any questions about this, about laying out memory, about making the bind system call, about finding these constants, anything related to this? Like everything we've demoed in class will get you through like level 7, I think, so far. Yeah, there's a question here.
What would you actually, instead of having everybody
Yeah, so that's a good question. The question is, how would we do it like maybe more correctly? Like instead of byte by byte, how do we do something that maybe like closer resembles this thing, right? Where semantically this first thing is a 2-byte thing. I think .2 is valid. So we just deleted one of the bytes. Let's see. Yeah, that looks good. X 16bx. Yeah, so now we got 0200 0050. So that works just fine. I think you can also say like dot short, I think is also in the land of C. If you wanted a 2-byte value, I believe it's a short value, which again, I don't think that means anything. That's why I don't use things like short, because how the heck are you supposed to know that a short is 2 bytes? That makes no sense. But that's technically it. It's complaining about the new line thing, but I think it's happy. Make, and let's do 816 bytes at this adder 0200. Yeah, that also works. So I would probably say byte 2 makes more sense. Or wait, no, is it 2 byte? See, it's not even that clear. The issue though is these values here. I think we can cut out these 8 null bytes and do .8 byte 0. So that'll at least give us that. We'll confirm that assembles. Again, I keep forgetting the new line. Yeah, so that assembles. That is giving us 8 null bytes in a row. This syntax, though, treats the number that's right here as a little endian integer. Like it's going to put it into memory as a little endian integer. So the issue here with these things is that we don't want a little endian integer. We actually want a big endian integer. So that kind of makes it trickier. So what we could do, so we saw before that 80 is hex 50. An option you could take is to say hex 50 00. So we've kind of flipped the order ourselves. And we've written it as hex so that we can kind of still specify byte by byte in this hexadecimal notation. if you think this is clearer, you could do this. There's a chance that the assembler supports some sort of big endian-like thing. Let's see. GNU assembler gas syntax big endian int. Let's see. I don't know. There's a chance that there's a way to do. I'm sure there's a way to do this. That is like more correct. That says, "Hey, give me a big endian value." I don't know. The docs for the syntax is not very good in my opinion. Generate big endian. Now, I think this is like a bunch of people saying how you can write assembly or some sort of code that will just flip all the bytes. But if we want to do it at assemble time, I don't know. I'm not very convinced about this documentation. Dot bytes, big endian. You might be able to say I want everything to come out as big endian. Network nets. I mean, next to these dot byte expressions, I'm not very convinced there's a good way to do it. Let's search for 2 more seconds. All right, yeah, I would guess there's a way to do it. I just don't know what the heck this syntax is to do it. So you could do it byte by byte, or in this case, again, we could do now a 4 bytes, and we could just flip it ourselves. It's easier if you're going to flip it yourself to write it as hex, because 2 characters is 1 byte in hex, and just flip it yourself. So we'll do 0, 1 is first, 0, 0, 0, 0, 7F. So 7F is 127. And now we get rid of all this. So now it's, yeah, so you just flip it yourself, and technically that works. Make test, make x8ex this address. Let's make sure that in fact came out. We wanted 16 bytes though. 20050 yeah, exactly. So this style works. So whatever you prefer though, it might be simpler to go byte by byte. But this is more compact at least. Any more questions? Yeah, there's a follow-up.
So, but like, is this the only way? Is there, like, when we would type like the logo, just type that, is there a way to do that like this?
Are you talking about, for example, like if you do dot string, hello world?
Is there a way for you to type just translate to the bytes for you?
To type it out normally. I guess I'm not understanding. Like when you say normally, do you mean like C? Like you want to type out a?
No, like if you look at the slide.
Yep. Right here, or the other one?
Yeah.
Mm-hmm.
Well, actually, I guess it's just. No.
Yeah. So I mean, like one, like in my opinion, something that might be more normal is to fill out a struct in C. And that's like the purpose of the compiler is the compiler, like you can write more clean code than assembly, I would argue. Probably most of you would also agree. You can write cleaner code in C than in assembly. It's much less verbose. And then it's the compiler's responsibility to translate that into the equivalent. Ultimately, all we need to do, the question is how do you represent it, is get these 16 bytes into memory somewhere. And there's various ways to make that happen. This is probably the most natural way of doing it with this particular assembler. There's probably other, like you could imagine writing your own assembler that supports like struct syntax, and like you could write, like fill in a struct like nicely. It's just like at some point, like you're getting closer and closer to the world of C where you just have like a computer doing the work for you, which is totally cool. Like that's the whole reason C exists, is it does all these nice things for you. Does anyone have any more questions about making this system call or any? Yeah.
There is no way to do it using move and registers?
You could also do this with registers. So, for example, we could allocate for ourselves, I think I learned the syntax is dot space 16. So dot space 16 means give me 16 bytes worth of space. It's just going to be null bytes here. And what you could do is move into, let's say, REX offset sock adder. And then you could move into, we'll say, word pointer REX. So this would be 2 bytes. Put a 2 there. Move into word pointer REX plus 2. Put 0x5000. Move word pointer REX plus 4. This thing, except this thing. Except now we don't want a word pointer, we want a D word pointer being 4 bytes worth of information. And
you go plus 6 then for coming from the base address?
so it would be at the base, we got 2 bytes, and then the 2 bytes further in. So this thing is, so right now we've written 4 bytes worth of information. So we would go REX plus 4. So from the base 4, start filling in, and then it would be question mark pointer, we'll figure out, plus 8, because we just put 4 bytes. So now we've got 8 bytes worth of information in, so we're filling in from the base plus 8. Does that make sense?
Yeah, that's how I was going about it.
Yeah.
First time, and then I built the first way to show they're down there.
Yeah, so I mean, this is a totally, and then we put a 0 just to complete that. So in this world here, we just filled in 16 bytes worth of memory. And this is a totally valid approach. You could 100% do this. The distinction here, though, I would say, is one is being done at assemble time and one is being done at runtime. Both are valid. This is just like making the computer do work that it doesn't necessarily need to do. I mean, if you can imagine writing a function or something that can like take in arguments and fill in this struct correctly, in which case you want to be able to dynamically respond to something. It's just at different stages of the process. And if we let's just confirm that this works. So this allocates 16 bytes for ourselves. So if we x/16bx at this address right here, all zeros initially. If we step, we just put this into REX. If we step one more time, we're about to write 2 bytes. So let's look at this address again. So 0200, step again. Now we filled in the hex 8 or the port, and then we step again and print print memory. Now we've got the IP address in there, and technically this doesn't need to happen, but you step again, and now we filled in the padding. So yeah, this is totally valid. It's just now you're doing it at runtime. Any more questions about this? Like if you haven't done level 2 yet, this is like 90% of level 2. So this is, if there's any confusion, like this is the time to understand it so that you're able to solve the challenges. Okay, cool. So this is how we fill in memory. So now we've seen really a huge chunk, as I said, of like the first half of this module, which is putting constants in to make system calls, and now putting memory in to make system calls. And then, I mean, this is the end of this slide. So we do a socket. So a socket, for those unfamiliar, a socket creates this socket thing. So it's like a file. It is, in fact, a file. It's a subtype of a file. Like hello.txt is a file. A socket is a file in exactly that same way. Or basically, it's a subtype. It just means it's a networked file thing that you're going to be able to, depending on how you set the socket up, sockets are very generic. You might be speaking over the network, and but ultimately what you're going to be doing is you're going to be doing read system calls and write system calls on that thing. Just like hello.txt, you could do read system calls and write system calls on. Just like a terminal, you can do read system calls and write system calls on to transfer data back and forth. So socket creates this thing. It's not fully ready to go yet though. Bind specifically says, all right, we've got this thing and I want to listen now on port 80 on this interface here. Listen says, I am specifically a server. So if I was a networked client, so we're not going to make you write a networked client in assembly, but it's actually a little bit easier than a server. You don't do a listen system call. There's just no, you don't need to. There's a connect system call instead. This just says, okay, put me in listening mode. So the kernel is like constantly running in the background like, do I have a new packet ready? Do I have a new packet ready? Have I received network traffic? Listen says, put this socket in that mode. Just start listening for network traffic. Now the kernel takes care of all that. It's very nice. This is why we have the kernel. The kernel does a lot of the heavy lifting here. And then we do an accept. So accept specifically means, now give me someone that has connected to my socket. So you've been busy listening. Now give me one of these clients. If there's not someone that has connected up to the socket over the network, no one has connected in, accept will just sit there and wait for someone to connect in. So if accept is just waiting, that means no one's connected. As soon as someone connects, accept will return a value. So in this case, we see it returns 4. If you've been paying attention to how these file descriptor things work, they just sequentially increment. So you saw we previously got a 3, that was a file descriptor. You got a good guess if you think 4 is probably a file descriptor. 4 is a file descriptor. It is also a socket. This is just now specifically not a socket that's in this listen mode waiting for new connections. This is a socket that is the bidirectional communication between the server and that specific client, and anything that goes over this thing, like reads and writes, that is these two people talking to each other. So as we see here, file descriptor 4 is also just a socket. And now what do? I mean, we don't talk about it specifically in this lecture. It's in the next lecture. We talk about it briefly. After we accept, I mean, we want to do something. If we're a web server, the very simplest web server implementation, right? So something you might have received is get/HTTP 1.0, right? Someone sends this thing at you. Think back to module 1. This is the simplest possible thing to send to a web server. I can just, and maybe it's a little bit confusing, I didn't even read. I can just like not even care what the heck this person is saying to me. I can just do the simplest possible response. I just say, HTTP 1.0 200 OK. I don't care what the heck you sent to me. You might have sent me, I think the slides even show this, right? You could have just sent a bunch of random characters and not even been valid HTTP. I don't care. I'm just sending you a simple HTTP response. And this is like the simplest possible web server here. Whatever the heck whenever you connect to me, I'm just going to give you an HTTP response. Now, it's not a very interesting web server. You might want to be able, maybe you can envision here like get/flag HTTP 1.0. You can envision what that web application is meant to do. This isn't what HTTP is meant to do. This is like, what is your particular web service meant to do? And maybe it's to give you the contents of a file. That's probably what comes to mind if you saw something like this. But it doesn't have to be. So you might imagine like you get this request that comes in. So after I accepted, I just read. So I didn't do the simple, like just give an immediate basic HTTP response. I did a read. So I want to see what the heck did this person just send me? They connected in. I want to see what they're trying to say to me. And hopefully, we're assuming very correctly in this module that whatever they're sending to me is valid HTTP. But you can imagine a client connecting in and not sending valid HTTP. We're assuming valid HTTP. And I get this that comes in. So now I've got this, after this system call, sitting somewhere in memory is the byte for capital G, the byte for capital E, the byte for capital T. This is just all sitting in memory. It takes 19 bytes just sitting sequentially in memory. And now this is just looking at it from the syscall perspective. You're going to need to do some sort of assembly to make this system call now happen, right? You need to figure out how to get in memory a register pointing at this slash and figure out how to turn this space into not a space. It needs to be a null byte because open takes a null terminated string. So this is where non-syscall assembly comes into play, right? We have a basic algorithm. We're just going to walk byte by byte until we find this slash, and then continue walking byte by byte until we find a space. And assuming that everyone is talking to you in the exact same nice structure, this will work just fine. So we pull that out, and now we can make a system call. We open that specified file. We read from that file descriptor, so that return file descriptor 5. We choose based on how we've decided to implement this program that we want to read from this thing now. In this case, we got 4 bytes worth of data sitting in this specific file. We were willing to read up to 256 bytes. Again, you could imagine the edge cases. There's all sorts of edge cases here, but what if the file is more than 256 bytes? You're right, this isn't going to work now. We'll have to keep reading or something if that was the case. We're just doing it very simple. Then we just write out HTTP 1.0 200 OK, new line, new line, new line, new line, whatever, this HTTP new line stuff, and then flag. And now this is a valid HTTP response. You'll notice here that I didn't include the content length header. So if you think back to valid or to standard HTTP responses, if you're going to put something in the body, 9 times out of 10, you're putting a content length to specify how long this is. Technically, in HTTP 1.0, you don't need a content length header, even though that's what everyone does. You don't technically need it. There's the client, if it's smart, and a lot of them are. In the case of this module, the client talking to you is smart. It just reads until there's nothing left to read. It just doesn't bother with this content length stuff. We could have said content length 4 if we wanted to be nicer. Instead, we just read until the end and then make sure that it's correct. And this is a valid HTTP reply. We clean up after ourselves. We don't even have to do this, but we clean up. We close file descriptor 4, which was that opened flag file. We could have closed 4 even before this write here if we wanted to. And then actually what we would do as well, we could close file descriptor. Oh, no, this is where we didn't close 5. That's not true. We didn't close the flag file. We weren't nice. We didn't care. We closed 4. And in closing 4, which is that socket connection between the two, closing that file descriptor, that means, okay, the network is done. And we'll talk about networking in a later module again. I keep saying that. This sends like a packet that says, okay, we're done communicating with you. So that's how the client knows that it's done, because the server closed it. The client gets informed of this, and that means there's nothing left. Does anyone have any questions about this? This is like almost the rest of the module, is figuring out how to implement this logic. There's really only, there's a whole bunch of reasons that this might be tricky, but the trickiest thing is figuring out how to isolate this path. That's like in the same way that we implemented stir length as a function, right? We wrote some simple little algorithm, right? Of the algorithms that exist out there, hopefully you would agree that stir length is one of the simpler ones. We need a simple little algorithm here that is doing very basic parsing. It's looking for a space, going one further, right? So we just walk memory until we get to a space, go one further. So now we have a register pointing right here in memory. And then we keep walking until we get to another space and turn this space into a null byte. And now this register that was pointing at the beginning is pointing at a string that is null terminated. And that is the thing you open. So it's you're likely going to have some difficulties with this, but just know that of the algorithms that exist out there, you've probably written way more complicated algorithms. Now, to be fair, you've written it in a higher level language than assembly. Hopefully, you'll agree that this isn't too bad of an algorithm to write. Find a space, find another space, turn the second space into a null byte, go one past the first space. Cool. Does anyone have any questions about that?
I'm trying to remember.
Yeah.
Null byte.
Yeah.
What you want.
Uh-huh.
But in assembly, I mean, ultimately the graphical strings like you can see,
Mm-hmm.
this new string volume goes to null byte.
Mm-hmm.
In this case, trying to remember what is the assembly that works on a set of data.
Yeah. So, for example, you can imagine, let's just assume, right, that we have register RAX that's pointer to memory, right? It's just pointing to memory. If we wanted to write a null byte right where RAX is pointing to memory, we would write move byte pointer RAX 0. That writes a single null byte right to this location in memory. Now, as the algorithm we just described, you're not just straight away writing a null byte. Probably you have a pointer right at this G for this get space flag HTTP 1.0. When you made this system call, you have a pointer to this capital G. Why do you have a pointer? It's the second argument to read. You specified where you're reading to. So this must necessarily be, before you do any parsing, RSI is pointing at this thing. It's the second pointer. RSI, so I said RAX before. RSI is pointer to memory, specifically start of HTTP request. This thing is pointing, because that's where you told read to read into memory. So if we did this right here, this would turn this capital G into a null byte. Now, that's not what you want to do, right? We want to walk memory. So we might, for example, have a loop where one of the things we're going to do is we're going to keep adding RSI1 jump loop, right? So this right here is walking memory. Now, you're not analyzing that memory. It's not that useful, and this is going to also run forever. But this, you can see that RSI, it's, at least for a moment in this very fast loop, it's pointing to one byte, then it's pointing to the next byte, then it's pointing to the next byte, then it's pointing to the next byte. Now, if we wanted to analyze this memory, what we can do is compare byte pointer RSI with 0, for example, if we wanted to look for a null byte. So in the case of stir length, we're looking for a null byte. Where the heck is my null byte? In the case of this algorithm, we want to look for a space. I don't think this syntax is correct. We'll confirm. Well, maybe it is. X8i loop. Yeah, it actually worked. So hex 20, I guess, it said that this space is a hex 20. Well, that's kind of nice. It's even more readable code. The character for the ASCII for space is 32, or as hex, it's hex 20. That's kind of nice. You can actually just put a space in there. I don't think you can do like AB. I don't think you can do 2 characters, but we'll see. Nah, that doesn't work. But you can do 1 character. That's nice. So rather than comparing for a null byte, we want to compare for a space. And I mean, in this case, right, maybe you jump equal done when you found a space. This would be a thing. This isn't the correct implementation for what I just said, but these are the building blocks of getting you there. Does that answer your question?
Yeah. Sterling, as long as you know where to start.
Exactly. Yeah.
You're returning the string of the flag.
So you don't even have to write this in like a functional sense of like returning something. You can even just modify memory, right? So these bytes are sitting in memory. Like everything you want for being able to open is currently in memory with the exception of a null byte.
Okay, so you're opening flag.
Right. So you don't have to like stir copy, for example, right? You can just modify memory and make sure your pointer is where you want it. Assuming you're not writing a web server that then later wants to also look at the original web request. We don't really care about the web request. All we really care about is isolating the single space separated thing and putting a null byte at the second and getting a pointer to the first. Does anyone have any questions about that? This will probably be the hardest part. I mean, there's different ways that you might make a mistake. But this is algorithmically the most complicated part. Cool. And as a reminder, when you inevitably make a mistake, because this is the whole point, this isn't supposed to be just trivial, use GDB. Step through this with GDB. So if I made my web server and I look at test and I run start I, this starts the program. Or you can use I posted in the Discord back when we were in the assembly crash course, my make file and my little GDB output thing, but you don't have to use that. Instead, for example, you can do display /4i RIP. And now every time you step with SI, that's showing you the next instruction. Another thing I would do, because this is terrible to look at, is set disassembly flavor Intel. That makes it so it doesn't look like this terrible syntax. It looks like this, which you're more used to. And now I can just step and watch things happen. And you can see right now I'm in my loop. So if I look at RSI is currently a null byte because I didn't write a very well-formed function. I just dumped this loop in the middle of my code. So this is about to crash, right? This is about to segfault because RSI is not pointing at a location in memory. So we step and we see segmentation fault. But if RSI was pointing to memory, so for example, let's say we did move RSI RAX just arbitrarily because this is a location in memory. And we wanted to debug this. We wanted to watch it happen, watch this loop go until it finds a space. We can run that. So we can make, we'll go back to normal GDB actually. Test start I, display 8i, RIP, set disassembly flavor Intel, step, and we can watch all of this happen. This is loading up memory as we did before. And now we're in our loop because as you see, the label loop is right here. If we look at RSI, that is currently this value. If we look at 1 byte in memory at RSI, it is the 2 byte. So 2 and 20 are not the same thing, so this jump equal should fail. So we see jump equal, that's not going to happen. So we're not going to be at done. We're going to be at loop +5 when we step. In fact, we are correct. This is the whole process of debugging. You keep saying your assumptions and what you know to be true. At some point while you're stepping through things, everything you're assuming to be true, one of those assumptions is wrong. That's why your code is wrong. Something you're assuming is correct is in fact not correct. So you need to just keep reaffirming to yourself what all your assumptions are about how this should be behaving and wait for the behavior to not do that. So then we step. So this is add 1 to RSI. So now, and then we jump to the loop. So now one of my assumptions, for example, is that RSI should be 1 further because this is how I wrote it. And we kind of saw that happen. It'd be very surprising if we were wrong here. But yeah, 402001, it's 1 further. If we print 1 byte of memory, x1bx at RSI, this is no longer 0x02. This is now 0x00, which again is not 20. So we should do another loop. And unfortunately, because of how we wrote this, we didn't write very semantically meaningful code. We're never going to find a space because this data that we just pointed at this thing is never going to find a space. Yeah, so that is what's going on there. Cool. Does anyone have any questions about this? Want to keep making sure if there's any questions that there's a question in the back. Yeah.
Can we use modules for something in this module?
So the question is, can we use pwn tools for something in this module? So pwn tools is for those unfamiliar, because we haven't talked about pwn tools yet, pwn tools is a Python library in the same way that requests is a Python library for being able to interact. There's a whole bunch of reasons you might use it. For being able to, for example, interact with a process. I'm going to say right now you're not probably going to find any value in pwn tools. In future modules, we'll bring up pwn tools when pwn tools might help you solve problems that might simplify what you're doing. But yeah, right now I would say pwn tools is probably not so useful. Cool. Any more questions about this? Awesome. Okay, one more thing, and I think we talked about this on last Thursday. One of the last things you'll do in this module, or somewhere near the end, what is it, like level 9? Yeah. Level 9 will ask you to do multi-process program that dynamically responds to multiple GET requests. So it's very common in writing a web server that you don't want to just be doing everything sequentially, right? If I'm doing this, if I'm opening /flag, that means I'm not responding to another web request simultaneously, right? I can only be doing one thing at a time when I've got one process running. As I'm hinting at through that statement, the solution to this is to run multiple processes simultaneously, and each process is doing some bit of work. I guess when I say that, as soon as I accept something, I want to be accepting another thing as quickly as possible. So like you could imagine, like these operations here, they run really quick. So realistically, you could run everything sequentially. This web server, it's a web server, it works. And if you implement it so that it loops and goes back to accept, you'll just keep processing a bunch of web requests sequentially. There's a whole bunch of reasons that you might write some web server where responding to a web request takes like a second. It might take a full second, which you might say, 1 second, who cares? That's like fast. In the world of responding to a web request, that is not fast. If you've got 10 million people connecting to you every second, right? If you're like Netflix or Google, you can't take 1 second for each web request and then just do the next one. You're going to have a huge queue that piles up and you're never going to get to everyone. You need to be simultaneously handling multiple web requests. A solution to that, obviously you can't necessarily handle infinite web requests, but if we, for example, just had 2 of these guys running at once, we would be able to handle 2 things at once, right? That's what that means. Alternatively, and there's reasons you can't necessarily do this. Like at some point, your CPU, even if it has 8 cores, 16 cores, 64 cores, can only do so much work. But you can start, as soon as you accept, you can spin off another process, and that other process takes care of responding to the web request, while the original process just goes back straight to accept. And that's what you'll be writing in level 9. And the way that we do that is with the fork system call. There's other system calls for being able to get another process created, but the simplest, I would argue, is fork. And we talked about on Thursday how fork just literally splits your process in 2. When you split in 2, you want one end of that jumping back to accept, and one end of that facilitating this web request and then exiting that process. And you can just do this. And now, even if each web request takes a full second and you get 100 web requests in 1 second, it's not going to take you 100 seconds to facilitate all those web requests. It's going to take you 1 second, assuming you have the CPU availability to, you don't actually need 100 cores to make 100 web requests happen simultaneously. Because maybe the reason it's slow is you're waiting on other things. So while you're waiting, you can stop working. There's a whole discussion of multiprocessing that you'll learn about in CSE330. But that is what we do later on in this module. And so the basic way that we do that, as we discussed on Thursday, is we fork. And the fork system call, if we look at fork is system call 57 and very nicely takes no arguments. It's just no arguments. We just call fork. And what's going to happen here, we'll write a very simple program for ourselves. We will move RAX 57. We will syscall. And then let's also just write something as we did before on Thursday. Let's write something to the screen. We'll do move RAX1, move RDI1. So that's the first file descriptor 1, standard out. We need some sort of buffer. We'll say offset hello. We'll make sure we give ourselves hello. RDX, well, hello only takes 7 bytes, let's say. I don't really know. Section.data, we'll say hello, and we'll say hello. What is that? 3, 4, 5, and a new line. So 6 characters. And then we'll do syscall. And as we showed on Thursday, if we run this, oops, we've got this missing. It's also complaining about something else. Oh, we didn't say .string. That's not a very helpful message, but we'll let it pass. And then we run ./test, and well, we didn't do an exit system call, but we did see hello happen twice, right? And the reason we saw it happen twice is there's 2 processes that are executing this code. Now we also want to do move rex 60, move RDI 0, syscall, and this is exit 0. Make test, ./test, no more crash, no more segmentation fault. Get rid of this, as we showed, right? Only print it once because there's only one process. We want to see this happen in GDB. Let's bring back our fork. And make test, gdb./test, start I, set disassembly, flavor, Intel, x4i, RIP. Ready to start showing things happening. If we step here and we step here, so we're currently, oh, I only did x4i, I didn't do display 4i. We're about to make this system call. Right at this system call, when we do this system call, the process splits into 2. One of them is considered the parent, one of them is considered the child. We do this. GDB kind of hints at the fact that this happens. It does hint at the fact that this happens. It says detaching after fork from child process 22503. The result of fork is sitting in RAX right now. That's as hexadecimal, as decimal 22503. We're currently stepping through in GDB in the parent process. Again, this, as soon as you start splitting off, it's like nothing's just sequential anymore. Things are happening simultaneously. It's a little bit confusing. Like you can see one hello already printed out. It's because the child process, which split off, just continued running because it no longer has a debugger making it run slow and instruction by instruction. It was just free to continue executing as it pleased. In the parent, we got the process ID of the child. But, I mean, maybe you're noticing an issue here. The issue is well, what if I want to debug the child process, right? I don't care about the parent process. I've already debugged the parent process. The parent process is doing what it's supposed to do. I want to debug the child process. There is a way to do that. So I believe sets follow fork mode child. You only get to pick one in this setup. I think there's probably a way to make it so you can have multiple debuggers attached. We're not going to get into that. We'll just say you get to pick one. We run set follow fork mode child, and we start the whole program again. So we're just starting it from the beginning. GDB lets us start from the beginning again. We run start I. It's already been started. It says, are you sure you want to start from the beginning? We say, yeah, let's run from the beginning. Now when we make this system call and we step through this, it's going to tell us, let's see what happened here. We stepped, it says, attaching after process 23284, fork to child process 23354, new inferior, whatever, process this, detaching after fork from parent process. Basically, it's saying I attached into the child, I detached from the parent. This hello right now, this came from the parent because the parent's no longer being slowed down by the fact that we have a debugger attached to it. And if we print RAX, RAX is no longer this 23354 whatever value. RAX is now just 1. It is? That's surprising. What the heck's going on here? Oh, well, we seem to have stepped one further and made RAX. Hold on. We'll get rid of this. We'll say not right here. Make test, GDB, start I, set disassembly, flavor, Intel, display 8i. RIP. And then set follow fork mode child. So if you want to debug in the later levels your child process, which is something you'll probably want to do because probably your child will be making a mistake and you want to debug that mistake, this is what we can do. So now we did this whole attach business. And if we print RAX now, it is 0. Why is it 0? Man fork return value. On success, the PID of the child process is returned in the parent process. So we saw that the first time when we didn't follow the child, and 0 is returned in the child. Return value goes to RAX. We followed into the child. 0 is now the return value that's sitting in RAX in the child. We can start debugging the child. I know that's kind of like a lot. What I'm going to tell you to do is when you get to level 9 and you have issues and you're wondering why the heck your child process isn't doing the right thing, go to Twitch or YouTube and rewatch what I just said on how to follow in GDB the child. This is how you do it. So it'll make way more sense once you're trying to debug your issues in level 9. Any final questions before we start wrapping up? Obviously, if you get stuck in this video also doesn't make sense, me speaking to you in the future, ask on the Discord. All right, thank you all for attending and good luck.